In this video, we are going to be doing example 11.10, disk and stick. Now, this problem is a huge pain in the butt, and you're going to hate it. But if it makes you feel any better, just think about how long it took me to type up and then actually make the video. Okay, so a 2 kilogram disk traveling at 3 meters per second strikes a 1 kilogram stick of length 4 meters that is lying flat on a nearly frictionless surface. The stick has a moment of inertia about its center of mass 1.33 kilograms times meter squared. A. Assume the collision is elastic and that the disk does not deviate from its original line of motion. Find the translational speed of the disk, the translational speed of the stick, and the angular speed of the stick after the collision. And then B, find the angular speed of the disk-stick system if the collision is perfectly inelastic. Okay, so first we have to keep in mind that for part A, we need to consider linear momentum, we need to consider angular momentum, and we need to consider kinetic energy. Since that's elastic, kinetic energy will be conserved. So let's start with conservation of linear momentum. So the stick starts out motionless, that's ms, starts out motionless, so it is not going to be on the left-hand side of the equation. The initial momentum is going to be the mass of the disk times the speed of the disk. And then it's going to be equal to the mass of the disk times the final speed of the disk plus the mass of the stick times the translational speed of the stick. So let's plug in some numbers and simplify it. The mass of the stick is 2, the initial speed is 3, and then the mass of the stick is 1. So we end up with that for simplification. Now let's see what happens with angular momentum. Now the initial angular momentum of the disk is going to be L equals mvr, and r is the distance from the axis of rotation. So when it hits the stick, it's going to be here. So it is 2 meters from the axis of rotation. We also know that using the right-hand rule, the angular momentum of the disk, both before and after, points into the page. So if you go back to this slide for a second, if you do the right-hand rule, so the first vector is r, it points down, and then the second vector is v, it points this way, you'll end up with your thumb pointing into the page. So the reason that's important is because you need to make sure you have a negative here. So we've got L equals mvr, I just put the r over here. So mass of the stick, mass of the disk, initial speed of the disk times r. And then that's going to be equal to the final, because if you look at the diagram real quick, the disk does not stick to the stick because it's elastic and it'll continue in its line of motion. So let's plug in some numbers and simplify. Remember, they give you the 1.33 in the problem, and you should end up with this for your simplification. Now, conservation of energy will also be conserved. We also have to remember that the stick will have both translational and rotational kinetic energy. So the initial kinetic energy will just be due to the disk. The final will have the final kinetic energy of the disk, the final translational kinetic energy of the stick, and the final rotational energy of the stick. So let's simplify, and we can plug in some numbers. So the 1/2 will all cancel out. And we'll plug in the numbers, simplify a little bit more, and we end up with this expression. Okay, so that was a whole lot of work, and you might not know exactly where we're going, but the point is here, we have 3 unknowns. Try to think for a second what our unknowns are. Well, our unknowns are the final speed of the disk, the final speed of the stick, and the final rotational speed of the stick. So you'll notice that now we have 3 equations and 3 unknowns. We have our momentum equation, we have our angular momentum equation, and we have our kinetic energy equation. So the first thing I'm going to do is I'm going to solve our momentum equation. I'm going to solve that for Vs. So you'll end up with Vs equals 6 minus 2 VdF. Then we're going to plug that into our K equation. So we're going to plug this in right here. I'm going to FOIL this out. We get this. Combine like terms. So what I did here is I subtracted the 36 over. 18 minus 36 is negative 18. And then I combined this term and this term together. And then there's no other like term, so we end up with this. So the next thing I'm going to do is I am going to solve for omega. And you get omega equals this expression right here. Now I am going to plug omega into the L equation. So if you plug it into the L equation, if you plug all this junk in right here, you get this. Now, the next thing I'm going to do 2 things. One, I'm going to add this over to this side, and the second thing is I'm going to put this 1.33 actually into the square root. So 1.33 squared is 1.7689, so I just want to multiply each of these terms by 1.7689. Then actually, sorry, this shouldn't be here because it's already multiplied into there. My bad. Okay, the next thing we're going to do is square both sides, and we should end up with that. So I just FOILed it over here, and then of course the square root sign just goes away. Then I'm going to combine like terms. So add this over to here, add these two together, and then take care of that. And you should end up with that. Now notice this is now in the form of the quadratic formula. So we can use the quadratic formula to get that VDF is equal to 3 or 2.33 meters per second. Now you may be asking yourself, which one should you use? Well, you need to use the 2.33 because remember, the initial speed of the disk was 3. So the 3 would be a scenario where it didn't hit the stick at all. And we know it did hit the stick, so this needs to be our answer. We can then plug that into our equation for Vs, which we got on the previous slide. So Vs will equal 1.34 meters per second. And then we can also plug this into our expression for omega. So solve that through. And this equation, let's just double check real quick. This is just the expression for angular momentum that we got on the previous slide. So again, this is just angular momentum being conserved. Plug in what we know, and you get that omega equals negative 2.015 radians per second. If you were having trouble with any of the algebra, please go back and double check your work and look at this video again. Okay, well, the fun isn't over yet, kids. We still have part B to do. So part B asks, what if it's an inelastic collision? So that would mean kinetic energy is not conserved. So let's start out again with conservation of linear momentum. So now we have the two masses sticking together. This VCM just means the speed of the center of mass. So we've got 2 times 3, mass of the disk times the initial speed of the disk, the two masses added together. The speed of the center of mass will end up being 2 meters per second. So the problem also asks us to find what the final angular speed is, and that's a little bit trickier. So we know what the initial angular momentum is. We got it in part A of the problem. It's just the disk going towards the stick. However, finding the final moment of inertia is going to be trickier. That's supposed to be a stick. I'm going to erase that because it's so bad. Erase all ink on slide. Okay. So here is our stick. So now the disk is going to be actually sticking to it. So not only has the moment of inertia changed, also the center of mass has changed. So the center of mass used to be here, now it's more like up here. So for the angular momentum, we need to find the moment of inertia of the stick with the disk attached. We need to use the parallel axis theorem. We know, because the problem gives this to us. There we go. Oh, and this should say, let's choose the center of the stick as our origin. My bad. So what I mean by that is the origin is here at 0. And then up here, that'll be at 2 meters. Because remember, the stick has a length of 4 meters. So the disk will be located at a location of 2 meters, and then the center of mass of the stick will be located at 0. So the new center of mass will end up being at 1.33, so somewhere around here, which is the same as 0.67 meters below the top of the stick. So we need to find the moment of inertia of the disk and the new moment of inertia of the stick, and then add them together to find our final moment of inertia. So the moment of inertia of the disk is going to be equal to mr squared. So the mass is equal to 2, and it is 0.67 meters away from the axis of rotation. So we get that. And then we need to use the parallel axis theorem for the stick. So this 1.33 is its new center of mass. So we get 3.1. And the final moment of inertia of the system will be those two numbers added together, which is equal to this. Okay, so we have conservation of angular momentum. The initial angular momentum is just due to, again, the disk traveling towards the stick, and the final angular momentum is I omega. So let's plug in some numbers, and if you solve for omega, you get -1 radians per second, and that is your final answer.